Okay, good morning, everybody, and welcome to week 11 of SDSU's Extension's Crop Hour webinar series. This week is dedicated to water, weather, and climate. I'm Dave Kringen, and I'm the Extension Water Resources Field Specialist in Mitchell, and will be your moderator this morning. So just a couple of housekeeping items before we get started. If you have any questions during the presentation, feel free to type it in using the Q&A feature at the bottom of your screen, and we will get those questions to our presenters at the end of their presentations. And also, you can check the chat feature as well, as I believe Sarah Botter will be providing some links in there that may interest you. And for those of you looking for continuing education credits or CECs, we will be displaying one QR code at the bottom or one QR code at the end of today's presentation. So there will also be a short poll at the end of the presentation with a couple of questions in it, and I encourage you to fill it out and let speakers know how they're doing. So, and also there'll be a longer survey sent to your email at the end of the week, so you can look for that as well. So with that, today we're talking about building water resilient systems through soil health and conservation drainage. Our first presenter is John McMain. John is an assistant professor with the SDSU Department of Agriculture and Biosystems Engineering. John got his bachelor's from Oklahoma State University, his master's and PhD from University of Kentucky. John specializes in water management, water quality, contaminant fate and transport, stream bank stability, low impact development, and extension outreach. And with that, John, take her away.
All right, thanks, Dave. We'll go ahead and share the old screen here and get the PowerPoints up. All right. You see the PowerPoints?
Okay. Yep, you're looking good.
Great. All right. Well, thanks everybody for joining this morning. As Dave said, my name is John McMain, and I am an Extension State Specialist here at South Dakota State University. Work in the field of water management and water quality, and end up working a lot with tile drainage systems and conservation drainage. And I also work on the urban water management side, and I like to say I'm an equal opportunity for water quality. So I think we all have a role to play with water quality and water management, and thinking about water at the watershed scale and how it affects our neighbors downstream. And so today, I'm teaming up with Anthony Bly to talk about how we can think about water resilience with both engineered systems as well as in-field or management systems that we commonly think about as soil health. And so I'll be covering the conservation drainage side, and then Anthony's going to talk about some new research that just come out related to soil health practices and how they improve soil structure and help us be more resilient when it comes to water management. So with that, I will also include my contact information up here at the front. So if you have any questions, you can grab this, contact me, follow me on Twitter, whatever, however you'd like to contact me. So I want to start with our pocketbooks. Where the rubber hits the road, a lot of times it comes down to economics. And in 2019, many of us remember that year, although in current conditions, it seems like a world away. But in 2019, it was an extremely wet year. There was flooding across the upper Midwest, South Dakota, Nebraska, Iowa, that caused significant damage from an infrastructure perspective, but also, and maybe especially from an agricultural perspective. And so no surprise, but over 60% of the crop insurance claims in South Dakota in 2019 were due to excess moisture. So that was 2019. It was an exceptionally wet year. And I've gotten some questions, and Laura's going to get into this tomorrow, Laura Edwards, about kind of how trends have been. But I want to lay a little groundwork for our discussion today. And this is a study that Chris Hay and Dr. Chris Hay and Dr. Dennis Toddy put together back in 2011. And they looked at the change of precipitation in two different periods. The first period was 1961 to 1990. And they compared that to the period from 1991 to 2009. And this map on the right-hand side, I'll just pull up the laser printer here, our laser pointer. So you can see these very dark, dark blue. So Northeast Iowa, much of the Eastern Dakotas, and Western Minnesota saw anywhere from a 2 to over 5 inch increase of annual precipitation. Now, so I'm from Kentucky originally, and on average we get somewhere in the range of 40 to 45 inches of rain a year, and 2 to 5 inches, it doesn't really make a difference when you're at 45 inches of rain. But when you're sitting at anywhere from 20 to 25 inches, that 2 to 5 inches could be as much as a 20% increase. And so when we think about the amount of change that we've had, it's been a wet period in the prior, that second chunk of time. And then we've seen several wet years since then as well. So that annual increase can make a really big difference. In addition to that, we're also seeing more intense storm events. So we've seen 14% more 1-inch rain events. So those kind of over that 1-inch threshold, we'd see more of those. And we're also seeing a change in timing. So we're seeing more coming in the winter when we don't have plants and evaporation that's pulling that back up into the atmosphere. And so that combination has led to a boom in tile drainage. And it's not, that's not the only factor, right? There's other factors related to technology and policy and different things. But this is how, much of the upper Midwest, especially the Great Lakes states and the traditional Corn Belt, has dealt with excess moisture. And a lot of times that excess moisture coupled with some impervious layer has led to a high water table. That high water table is dealt with by tile drainage. And so as we see those trends of increased moisture, especially in the Dakotas and Northeast Iowa, even down into Kansas, that has resulted in the largest percentage increase in tile drainage. This is from 2012 to 2017 in North Dakota, Kansas, and South Dakota. So South Dakota has seen a 69% increase in the amount of acres tiled from that 2012 period to 2017. And I don't expect that to change. And the challenge, though, is a lot of this moisture is coming when it is a hindrance, right? It's coming either in the fall or in the winter. So we end up with excess in the spring. And we don't really need it in the fall, winter, and spring. We need it in the summer. And so if there's just a way that we could use this excess moisture, conserve it as a resource, and then be able to apply it back into the fields or hold it in the fields when we need it, that's where we could, really take advantage of this increasing trend in precipitation. So with this change in amount and change in timing, we end up with a timing mismatch. So the water's there, maybe on an annual basis that we need, but it's not there when we need it. And so 2018, if we think back, that was also a relatively wet year in South Dakota, excuse me. And so not surprisingly, almost 35% of the crop insurance claims were due to excess moisture. But interestingly, almost 20% were due to drought. So in the same year, in the same state, we had conditions that led to crop failure or loss of productivity due to both moisture and due to drought. Now, if we go back another year, 2017, that was a dry year. So unsurprisingly, over 35% of the crop insurance claims were due to drought. But again, same state, same same year, and the second leading cause was due to the exact opposite end of the spectrum, excess moisture. And so this pattern is being repeated. 2019 was exceptional, saw excess moisture, and there was no crop insurance claims due to drought that year. But in the preceding 2 years, we saw the leading two causes were on opposite ends of the spectrum. Excess moisture in 2018, second to drought. And then in 2017, drought was the leading cause, second to excess moisture. Now, this is just again, kind of reinforcing this, and this isn't really a fair picture, right? Because it's two different locations, two different crops in 2 different years. So we're not comparing apples to apples at all. But just to reinforce the idea, in each year, we could either deal with excess moisture or not enough moisture. And so we have to be, our systems have to be resilient to withstand both of those extremes. Now, this is a really kind of straightforward graph. Chris Hay made this, and this is looking at, on the y-axis, we have precipitation or rainfall and snowfall, and then evapotranspiration. And if you're not familiar with evapotranspiration, it's essentially the how much water goes back up into the atmosphere. So we're pretty familiar with evaporation. That's what, evaporates out of a pond or a lake or whatever. It's the water that the energy from the sun pulls back into the atmosphere. And then transpiration is related, but it's the water that gets taken up by a plant's roots and then gets transpired up into the atmosphere through the leaves. So ET, or evapotranspiration, is the combination of those two, evaporation and transpiration. Now, for most of the year, the blue line here, or the upper line in the first part of the year, precipitation is higher than the evaporation and transpiration, that evapotranspiration, or ET. But then we hit June, middle of June, and we have the break points, and then evapotranspiration is higher than the precipitation. So in essence, the first part of the year and the last part of the year, we have too much water, potentially. And then in the middle part of the year, during the growing season, we don't have enough water. And so this creates a potential for both engineered solutions as well as changes in management that can take advantage or optimize kind of how we're working with either too much or not enough. And so we think about too much water, we can think about drainage or soils that, encourage infiltration. Or if we think about the ET portion, where we need either controlled drainage or irrigation, or soils that can hold more of that water. And in addition to kind of the normal pattern that we just saw, we also see more extreme events, and more extreme events have led to things like flash flooding, flash drought, and that's kind of the short term. And our reaction to these short-term extremes ends up being, building protective infrastructure or basin scale water management. With drought, it would potentially mean adding in irrigation or crop insurance or soil resilience. But in essence, a lot of these traditionally have been reactive, but we want to think about ways that we can be proactive to both too much water and not enough. Now, this is some data from a study, the Transforming Drainage Project, and this manuscript is currently kind of working through in preparation to be published, but thinking about when tile drain flow occurs. And so it's not a surprise to us kind of in the upper Midwest that in general, most of the tile flows in the spring when you're in the north, because the ground is frozen. And so you really don't have much flow in the wintertime. But then when things thaw out, then tiles are flowing. But then kind of when you move to the maybe more temperate zones, and we group these by plant hardiness zone. So kind of in the 5B plant hardiness zone, we see most of the flow in spring and winter. And then when you get into the 6A and 8A plant hardiness zones, the warmer climates, we see most of the flow occur in winter. The reason I want to bring this up is because this provides an opportunity. We have too much water in spring and winter, and so that gravitational flow is leaving through the tile. But that water that we treat as a waste in the spring and winter, that's a valuable resource when we hit summer. And so if we can think about systems that are able to capture and store or hold more of that water in the soil, then that enables us to use that water as a resource when we need it. And it's not just water, but it's also nutrients. So with that tile being lost, or with that drainage being lost, typically what we see is most of the nutrient loss also occurs in the spring. And so again, holding more of that water either in the soil or in some type of edge of field practice, that enables us to not just hold the water as a resource, but also hold the nutrients as a resource. So let's bring into the picture conservation drainage. And conservation drainage is essentially a philosophy that allows us to have the benefits of tile drainage and subsurface drainage, managing water while addressing water quality and flow impacts. And this is both at kind of the watershed scale as well as at the field scale. Dr. Laura Christensen from University of Illinois, one of the leading experts with wood chip bioreactors, her definition of conservation drainage, it's a handshake in the field. So basically balancing the benefits that we get from agronomic productivity of tile drainage with being a good upstream neighbor, making sure we're not losing nutrients and water, and also using conservation drainage to improve resilience for our own fields. So the next few slides are going to be from the Transforming Drainage Project. So it's an 8-state project. It just wrapped up 5-year from USDA. And the neat thing about this was it included a huge range of different practices across all across the landscape. So we ended up with 70 plus site years of data for the different practices that I'm going to talk about today. So the 3 practices that we focused on for the Transforming Drainage Project were saturated buffers, controlled drainage, and drainage water recycling. And saturated buffers I'm going to introduce those. I'm not going to spend a lot of time because we don't have direct crop benefits with saturated buffers. But in essence, with a saturated buffer, what you have is a control structure, which is close to the ditch or the stream. And that control structure diverts water into a lateral that runs parallel to the ditch or the stream. And so as that water goes into that lateral, then instead of just flowing directly into the stream as it would before the control structure was there, it flows into these laterals, saturates the riparian area or the buffer between the lateral and the stream, and then it flows through that soil and vegetation until it ends up in the stream. So we're able to get water quality benefits primarily, but we are also able to see some storage benefits in the landscape. And the kind of predominant mechanism for nitrate, specifically removal, is denitrification, but we also get some plant uptake, and this is usable land still, right? It could be used for either haying or any type of really edge of field work. So, it could be habitat as well. It couldn't necessarily be used as crop ground, but it could be used in a way that you could still get some working land benefit from that. Now, from a nitrate load reduction perspective, we see these perform on average pretty well, especially for the low cost to put them in, 40 to 45% on average. And but a huge range. And a lot of this depends on the amount of flow that's coming in to the system. So if your tile is flowing more than you expected, or you add additional lines onto it so you have a bigger drainage area, then most of that flow is going to end up bypassing the saturated buffer and not being treated. But of the water that's treated, it does a very good job of treating that nitrate. Now, controlled drainage. So controlled drainage uses the same control structure perspective. So you have, again, laterals draining the field, going to a main. That main would normally just outlet directly into a stream. But now you have a control structure in place. And that control structure has removable boards that you can raise and lower the water table within the soil profile. So this gives you an opportunity to hold some of that water in the field when you don't need drainage, right? If we have most of our flow occurring in the spring and winter, or in the spring for the upper Midwest, then we could hold that water in the field, maybe drop it some for planting, to be able to have the benefits of timely planting and not mudding in a crop, as they say. But then maybe add some boards back, not to the point where we drown out the roots, where we would lose our drainage benefit, but maybe enough that now we have a reservoir there. If we have any timely rains in June or July, we can hold those for when things get really hot in August. So it gives us more control, that's the term controlled drainage, of our drainage system. And primarily the initial thought of this was nitrate, and I'll talk about that on the next slide, but we also have the potential to have a yield benefit from controlled drainage. Now, this graph is a little hard to consume if you don't know what you're looking at, so let's just walk through what we're looking at in this graph. Okay, so on the x-axis on the bottom here, we have the ratio of the growing season precipitation to its long-term average. And so in essence, if we're on the right side of one, that means the growing season in which that was measured is wetter than normal. If we're on the left side of one, it means it's drier than normal. And I should say, so all of these dots represent a comparison between controlled drainage and free drainage at the same site, under the same conditions, same crop and everything. And again, it's from across that wide, those 8 states, wherever we had controlled drainage, wherever we had that comparison, each site and each year represents one dot. And so then on the y-axis, this is the ratio of yield of controlled drainage to the yield of free drainage. And so if we have higher than 1 or above 1, then the controlled drainage yielded better. If we have lower than 1, then the free drainage yielded better. The controlled drainage yielded worse than the free drainage. And so what we see is a lot of, in many cases, there wasn't a huge difference. And especially kind of around this, if it's an average precipitation year, we don't see a huge difference. What we do see, though, is a pretty significant grouping when we had drier than normal conditions. Our controlled drainage yielded better. And then on the wetter than normal conditions, it was kind of across the board, but typically we did see free drainage yielded better than controlled drainage under wetter than average conditions. And it's not necessarily due to the control drainage technology itself. It's more due to how we recommended management. So the conventional management for a long time has just been, set the board at the beginning of the growing season and leave it for the rest of the growing season. Maybe go out and lower it when you need to get in for field operations for harvest. But otherwise, don't worry about actively managing the boards. And so what this research has showed us that active management is pretty key to effectively getting a yield increase with controlled drainage. And you can see that, even in wet years, there was the potential to have a higher yield with controlled drainage as compared to free drainage. And again, remember, a lot of this is about timing. It's not just if we have a wet year on average or overall. It's when we get the water that really makes a difference. And so we can see, though, if we are effective managers of the controlled drainage, we can see yield increases. So 1.1 would be a 10% yield increase, 1.2 would be a 20% yield increase. And so for the most part, we're kind of between this 5 to 15% yield increase for controlled drainage. So there's the potential, if well managed, if actively managed, then we can hit pretty good yield bumps, 10 to 15%. Now, current technology, I don't think we can do that. If it's up to the farmer to go out and move those boards based on information, maybe incomplete information that they're getting, that's not good enough, because a farmer has 50,000 things to think about, especially during the growing season. There's spraying, there's walking the fields, there's a lot of stuff to think about. And so what we're working towards is automating these systems based on a lot of the information that would affect crop growth. So how moist, what's the soil moisture in the field currently? What's the weather forecast? Do we expect more water to be added to the system from weather? What's the crop growth stage of, where are we at in the maturity of the crop? How much water does it need? And so all of these things can be used to automate this system. That's what we want to move towards, to take out the guesswork and really allow us to manage for, yes, if it's too wet, lower the boards, let some of that water out. If it's too dry and we anticipate it's too dry, then raise those boards up and give us as much storage as we can to when we hit our dry spell. Now, from a nitrate load reduction perspective, most of the nitrate reduction comes with reducing volume. So again, we're holding that water back when we don't need drainage. And so because of that, we're reducing the volume of water leaving the field. So we get a pretty good load reduction, but just from that. There is a pretty handy kind of screening tool. It's on the transformingdrainage.org website, and you can look at how appropriate your land or potential tiled land would be for controlled drainage. And so you can look at it. It takes into account slope, seasonal high water table, land use, and then how much of that area is together. So if it's a field area, and this is you still need to go through design and things like that, but this is kind of a screening tool to think about if your system is a good fit for controlled drainage. And I want to say one more thing about the suitability of controlled drainage. So you can imagine if you're backing water up and you're on a flat field, then you can control a lot of the land area with one control structure. But now let's say you're on a pretty sloping field. Well, that control structure is only going to back up to a certain elevation. It's not going to back water uphill. And so you're going to be limited in how far back you can manage that water. So this is best suited for relatively flat fields, or if you tile along the contour, that works better than if you're tiling down the contour and have to put control structures, kind of throughout the field. So the next practice, the third practice that we'll talk about, is drainage water recycling. Now, in this case, this is kind of the maximum amount of control you can have from a drainage and irrigation perspective. And really the concept is simple. It's in essence taking the water when we don't need it and holding it, and then using that water as a resource when we do need it. And this can either be done via sub-irrigation through the existing drainage system, which Dr. Tom Scherer talked about on Tuesday, or it can be done through a more traditional overhead pivot type system, in which case, it would follow kind of standard irrigation patterns. This can be used as supplemental irrigation. It can be used as, the complete irrigation, but it's likely you're going to run out of water at some point if it's the only source of irrigation. And in essence, it's two pieces. One is you can have kind of marginal increases of crop growth, but then there's also the case of if you got just 1 or 2 inches at a certain time, that might mean the difference between a crop success and a complete crop failure. And so this gives you kind of a better buffer between those weather extremes. So, in essence, if you have that 4-inch July downpour, a lot of that may be lost downstream, but drainage water recycling allows you to hold that in an impoundment and then put it back on the field when you get that subsequent 4-week August dry spell. Now, again, biggest question, does drainage water recycling consistently increase yield? And again, there's a lot going on in this figure. Let's walk through it. On the y-axis here, these are, again, the site years from either drainage water recycling or a free drainage, a conventional drainage. So again, it's a comparison between those two systems, and each line here represents 1 year at one site where those two systems were compared. And then the dark lines are where drainage water recycling had a yield advantage. The gray lines are where free drainage did better. And then the length of the line is how much better it did. So it's broken down into dry years, normal years, and wet years. And so in general, we saw a 69% yield increase, 69% of the systems had a yield increase with drainage water recycling and dry. 61% had a yield increase in normal years, and then 58% had a yield increase in the wet years. So even in wet years, we still saw the majority of systems had a yield increase with drainage water recycling. Again, it's not about the total rainfall, it's about the timing and when we need it. And the amount of yield increase in dry was 59 bushels an acre. In normal was 41 bushels an acre, and in dry was 17 bushels an acre. And then if we look, so again, thinking back to management and that controlled drainage, a lot of times when we saw free drainage perform better, it usually came back to management, not being able to get enough information and make a good enough decision in a timely enough manner to make a difference. So we see the same thing with drainage water recycling, but you can see that the bars where free drainage perform better are much smaller. So it's a much closer difference than when drainage water recycling performed better. There is a really handy tool that transforming drainage group also put out, and it basically is a decision tool about you can size your pond, you can put in your crop, you can put in different rainfall data, and this will give you the information about the payoff and like, is it worth it to think about putting in a drainage water recycling system. So this is a really handy tool. I'd recommend you check it out. And then these are a few more different resources. This is the first one is the Transforming Drainage Project website, which has all the tools that I talked about. This is the data set from the Transforming Drainage Project. Conservationdrainage.net is the kind of what we're evolving into. It's a group of academics and industry that are kind of working toward conservation drainage objectives. Then the ADMC, the Ag Drainage Management Coalition, is an industry-led group that has a lot of really good resources. And then Anthony and I are actually co-hosting a podcast coming out of SDSU Extension that will be published soon. And our first season is actually on conservation drainage. So we cover all of these practices and more in depth. So we'll have about 16 episodes on conservation drainage practices. And so this is where I'm going to start to transition to think about soil health and how infill practices can improve, our ability to be resilient, weathering these extremes, either extreme dry or extreme wet. And so under conservation drainage, I talked about 3 structural practices, but there's a lot of benefit that can be had from infield treatment. And, here's a really good list: perennials, cover crops, improved nitrogen management. It all starts about what we put in the field and then how efficient our crops are at using what we put in the field. And a lot of times too, it seems like tile drainage and soil health butt heads. And I would say, it's not necessarily an either or. I don't think we should look at it from that perspective. I think we should look at it as what fits our system best. And, how can let's think about our objectives. One objective is, of course, agronomic crop productivity, but then we also think about, water quality, water quantity, and how resilient our systems are. And so tile drainage and soil health, I think, are both tools in the toolbox, and we want to use them judiciously or deliberately in a way that helps us achieve those objectives. I think soil health, can be used in almost any application. But if we're dealing with a high water table situation, maybe there is a cause to think about if tile drainage would also help that situation. This is a study, long-term study from Purdue, Dr. Eileen Klodivko. And this comparison of pictures is very striking to me. And this is kind of what I'm talking about. So this is a tiled field. It's a field that the underlying high water table issue has been resolved through tiling. And then this is a field that is not tiled. Now, I'm not saying tile is the answer in every situation by any means, but in this case, our soil health practices actually did significantly better. We had 3,100 pounds biomass per acre of a cover crop, cereal rye, when we were able to manage that underlying high water table issue with tile, compared to the 700 pounds of biomass per acre that we weren't able to manage that underlying drainage issue. And so on the flip side, though, if poor drainage is due to poor soil health, if it's due to poor soil structure, we're not getting infiltration, maybe we have crusting, maybe we have a really high bulk density from extreme tillage and compaction, then tiling is really not going to address that issue at all, because you're more worried about water getting down to the tile, and that's a soil health issue. But if the poor drainage is due to a high water table. We have some impermeable layer that's preventing water from going any deeper, and so it just gets down there and stays, then it's going to be harder to establish soil health practices. It's going to be harder to grow cover crops, as evidenced here. It's going to be harder to do no-till if we have those kind of perpetual high water table issues. Now, 2 more slides and then Anthony's going to take over, but how do soils affect water? So if we think about the water balance, we can think about, okay, water, rainfall comes and it lands on the ground surface. And I should have put infiltration first, but so first water goes in, has to go into the soil, has to infiltrate into the soil. And the main thing that's going to drive that, well, there's a lot of things, but bulk density is a characteristic that we can control and improve through improving soil health. And so that's where, right off the bat, we could be shooting ourselves in the foot if we're not able to even get the water into the soil. Once it's in there, we want it to stay, or we want it to be available to plants, but not be so much that there's no air that the roots can, grow. And so bulk density and organic matter are going to affect that water holding capacity. And then once it's in there, we think about water moving through the soil. So that's going to be soil structure, macropores, and bulk density as well. So basically, is the water able to get through the soil? And we know that soil health practices can improve this. And then one that we don't often think about is evapotranspiration. So if you have a cover crop that goes in at the end of the season or towards the end of the season, that cover crop now has the potential to use excess water whenever it can. So it's not going to grow in the winter. It's going to be dormant, but you're going to get some evapotranspiration that you wouldn't necessarily get. And you're adding carbon into the soil. So going back to the water holding capacity and infiltration and percolation. So thinking about a big picture, as we showed at the beginning, and as Laura's going to touch on tomorrow, weather extremes, they're likely not going to go away. And so conservation drainage could provide field and watershed scale benefits. Conservation drainage has the ability to increase resilience and reduce downstream impacts. Dr. Jeff Strock has a really nice saying that I like to use: there's no silver bullets, but there is silver buckshot. So there's a lot of potential solutions, and it's figuring out what works best for the situation and for our objectives. And then again, we saw the potential for controlled drainage water recycling to be really effective for improving yield. So thinking about yield from a agronomic perspective and a water resilience perspective, they work. The mechanisms are sound, but we need to move toward more active management, maybe automation. And again, edge of field practices are tools in a big toolbox. Now we're going to hand it off to Anthony to talk about some research about infill practices and how those really help the water holding capacity and the water movement through soil helps us be more resilient.
Yes, good morning. Yes, my name is Anthony Bly. Just as a reminder, I'm a soils field specialist with SDSU Extension, and so I've got the benefit of sharing with you some research done by soil physicists at SDSU, and those would be Navdeep Singh and Sandeep Kumar. And so they've really focused on soil health while at SDSU. One interesting thing that they did is used X-ray scanning to look at our soil and verify or visualize some of these things that Dr. McMain just finished talking about. So in soil health, we focus on bulk density and porosity and water movement. And so this is the paper. It was accepted in the Soil Science Society of America journal, which is really a leading soil journal. And the title of the paper was Grasslands Conversion to Croplands Impacted Soil Pore Parameters Using X-ray Computed Tomography. And basically that's CT scanning. So when you go get scanned and you lay down and you're in that donut, that's exactly what these researchers were doing with the soil samples that they took. Here they are on the left, Dr. Kumar, and on the right, Dr. Singh. And my part with working with them is, finding fields, locating producers, and helping them find their way to some of these special places. And so it's been a privilege for me to work with NavDeep and SandDeep, and this very enjoyable. So what they did, and I like to point out that this is about 5:45 in the morning, and they'd already left Brookings and traveled about an hour and a half to get to a field. And so very passionate about what they do. Here they are taking the samples in the field. SandDeep there is driving a what we call a Uland soil core. It's just basically a cylinder into the soil. And NavDeep has removed that and is labeling that, and they'll take those soil cores back to the lab. So there's a picture of that core. It's basically encased in plexiglass with some kind of corky material on the top and the bottom. And then on the right side there, I mentioned that CT scanner, that X-ray scanner. There's that soil core laying in the scanner, if you will, and they took those images, multi-images of that core. So really a innovative new technique to use to look at soil. And we can't see below the soil surface. We'd like to. We try to explain all these soil health advantages, and we've measured them in the lab, and we use numbers to convey those differences. But this is a neat visual. And so this is what they found out. They had 3 systems that they compared, and these samples were taken across the fence, if you will, from different producers' fields. And so the first field that they sampled was this conventional tillage corn soybean rotation. So that's typically what we do in eastern South Dakota. And so what the dark green or the filled in areas in that core are showing are the pores, open spaces. So not the minerals or not the solids, but the pores is what they're showing. So you can see there's a good amount of pores in that conventional tillage system. It's been loosened by the tillage and whatever. But below that is a long-term no-till system in a diverse crop rotation. Cover crops when the farmer could get them out there, mainly after the oats in that rotation. And this producer also grazes. And so we think about the soil health principles. Basically, all of them were covered in this treatment, as we would call it, or in this system. And so you can see a marked increase in the amount of porosity in that soil health system. That's what I'm going to refer to it now, versus the conventional system. They had the luxury at this site to compare it to native grass, which was a well-managed pasture that had never seen any tillage. And so you can see that on the right. You can see even more porosity there in the native grass, even compared to the no-till. So we see a nice increase from the conventional system to the soil health system, and then a further increase to the native grass system. So there you are. It's visual and very good look at that. So some other things that they did is they did verify what they were seen with the X-ray with the traditional soil physical measurements. And what I did is took their paper and converted it to units that we're accustomed to thinking about. Porosity is a difficult one, but I think you can understand that. The percent porosity is the percent of the volume that they measured that's actually pores. And so we see that the soil health system at 57%, the conventional lower at 49%, so reflecting what we saw in the X-ray, and then the native grass much higher at 67%. Bulk density also just closely related to the porosity, actually the opposite of porosity. So the treatment with the lowest porosity has the highest bulk density, and I converted that to pounds per cubic feet of material. So which one would you rather shovel? And you can notice this if you go out into a tree belt or a grove or maybe into a native grass pasture and you just start digging a hole and shovel, you will notice the soil is much lighter, if you will, in those two cases versus digging out in a field that's been tilled a lot. They also measured internal drainage, or what I call internal water movement. I converted that to inches per hour. So that's a movement of water within that soil core. With that soil health system, we're at about 4.7 inches per hour. With the conventional system, less than an inch. So the effect of that porosity is very evident with that internal water movement. Of course, that native grass way up there at 8.2 inches per hour. Another really close soil health indicator, also related, as Dr. McMain said, about water storage. We know that soils that have higher carbon contents are able to store more water, and we see that evident here with the carbon in these systems, just under 3% in the conventional system, 3.34% in the soil health system, and over 4 in the native grass. Now you may say those aren't very big differences, but remember, this is soil organic carbon. So converting that to organic matter, we multiply those numbers by a lot of us say 2, but actually it's about 1.65 or 1.7 to get organic matter. And so little bitty differences can make a big difference. So there we have the actual scientific measurements verifying what we saw in the X-ray scans. One thing that I further did was we often look, when we take Soils 101, we look at the ideal. We call it ideal, and I'm changing my notion on that of what an ideal soil is. It's more like a conceptualized soil. So if we use a pie chart to show that 100% of that soil, we'd like to see half of those as minerals and organic matter and carbon, and then the other half is pores. Ideally conceptualized, I guess, is a better way to show that. So I took the actual numbers and applied them to the pie chart. So the conventional system, has about 46% there of the space taken up by minerals, and another 4.8% taken up by organic matter, and we have less than 50% as pores. And I've just shown half filled with water and half filled with air. We didn't measure the water content of these soils, but that's just the way I'm showing it on the graph. So if you look at the soil health system, we have much more porosity, don't we? Because we have less of that space taken up as the minerals and the organic matter. So we have much more water storage capacity for those times when we do dry out and we need that water to support our plants. But if you look at the native grass, oh my goodness, a lot of porosity. And if you go out and dig in a well-managed native pasture, now it has to be well-managed. I mean, there are pastures that are overgrazed, and so the benefits of soil health are somewhat reduced. But in this case, a good example of good grazing, and we see roughly 40%, 39% of that as the solids, and the rest of it as pore space. So awesome home for microbes and nutrient cycling and water storage and air and water exchange. So very strong correlation here to what they saw in the X-ray scans. So it's just been my privilege to be able to work with Doctors Kumar and Singh, and the science is absolute proof that conservation practices improve soil health parameters. There's no doubt. And so again, I'm extremely thankful to have the opportunity and to share this with you today. And thank you for inviting me, John.
Okay, thank you, Anthony. I'm sorry I didn't get to introduce you. I thought there was going to be some space in between presentations. So
that's okay, David.
We all know you though, Anthony. So if you have any questions, go ahead and put them in the Q&A feature. I don't see any at this time.